Relax, relax. I know we are taking time or taking step, right, to actually fill in the electrons, the orbitals at the high school level as I promise you. But then, if we rush, we are going to crash. So we need to take our time and understand the thing bit by bit. So far you know about orbitals very well. But then we are almost there to fill them with electrons. But then we need to know that there are principles that govern how we fill them with electrons. Right? So we need to today we are going to look at those principles. The principle that govern electron configuration or how we enter electrons into the orbitals. There are some principles that govern that, and let's take time to do that. So, majorly, the major focus ones, principles, there are three in numbers. We have three major principles that are governing this. But then there's an additional one I will be adding at the end, which is also very, very important and which is very critical, but they don't actually stress much on it, but it's actually active every time. So let's keep in touch. So what are these principles, right? These principles are three, as I said. One is the Pauli Exclusion Principle, the Aufbau Principle, and the Hund's rule of maximum multiplicity. These are the three major ones that govern electron configuration into the orbitals. And then there's an additional stability principle that we'll talk about. I said that we are going to. So let's take these principles one by one in relation to how they are used, what they mean, what are they saying, right? So let's start with the Pauli exclusion principle. So Pauli's exclusion principle states that the maximum number of electrons that can fill any one orbital is 2, and they must be of opposite spins. So see, how many orbitals do we have now? So let's say we have talked about S orbital, right? I say it's going to be a box. So for S, it's going to be a box. For the p orbitals, right, is p, we say p is a degenerate orbitals. We explained that in the previous session. So they have session. So this p orbital. So this is a px, py, and then a pz, right? So they are, this one has 3, and the d orbital has 5, right? 5 suborbitals, right? 1, 2, 3, 4, 5, right? So this is d. So you call this one d1, d2, d3, d4, and d5. So there are basically 2 types of orbitals. We have the non-degenerate orbitals and degenerate orbitals, right? Whatever principle that we are going to apply on these two, apply to all of them. So I'm going to be using these two in the meantime. But we are saying that the maximum number of electrons that can fill any one orbital is 2. So when I'm taking a one orbital here, I'm referring to each box. If you have this box here, this box here, this box here, this box here, then maximum number of electrons that can fill any of them is 2, and they must be of opposite spins. What do we mean by opposite spins? So here, in order to represent electrons, we are no more going to use the dot, right? We are going to use something like arrows, right? A half-side arrow or one-sided arrow. So or an arrow. So this is how an arrow look like, right? But then for our electrons, we are going to clean one of the arrows, right? And then just put it like this. So this is like the arrow showing up, and then the other spin is going to be like this. So it's an arrow. This is a separate, this one electron, and this another electron. It is in this format that we'll be using to fill these orbitals. Right, so these things that you are seeing here are electrons. So this is how we are going to be. We are no more going to use the black dots again. Okay. We are saying, so the spin up and the spin down, right? The maximum number of electrons that can fill any one orbital is 2. So if you take one box, you cannot have 3. You cannot have 4 electrons in one box. You can have 0, you can have 1, you can have 2, and that's it. You stop there. You cannot fill it up to any other number. So the maximum number that can fill any particular box or orbital is what? 2. So that's what Pauli's exclusion principle is saying. And these electrons that are in that box should be of opposite spins. So basically, if you are referring to the s orbital, right, the maximum number of electrons, you have one, it must be of opposite spins. This one too should be of opposite spins. This one too should be of opposite spins. This one opposite spin. But the maximum number of is what? So the s orbital can take a maximum of 2 electrons. The p orbital in general, there are 2, 2, 2, and there are 3 subsections, right? So the p orbital will take a maximum of 6 electrons because 2 will go here, 2 will go here, 2 will go here, a maximum of 6 electrons. So what do you think for the d orbital? So there are 1, 2, 3, 4, 5 boxes, right? It's going to take a maximum of 10 because each each box is going to take a maximum of 2 times 5 is going to be 10. So basically, that's it, right? That's what Pauli's exclusion principle. So with Pauli, at the Pauli level, we know that the maximum number of electrons that can fill these orbitals is 2, and they must be of opposite spins. As simple as that. And we understand what we mean by the opposite spins. When one is going up, the other is going the other way, right? That the opposite direction. Okay, now let's go to the second one, which is Aufbau's principle. Aufbau's principle is saying that in filling of atomic orbitals, orbitals of lower energy are fully filled first before orbitals of higher energy. So the major orbital that we look at are S, P, D, and F. So mind you, this one, it is going in a direction of increasing energy. The energy of this guy is lower than the energy of P, the energy lower than the energy of D, lower than the energy of F. Generally, this is a general statement we are giving. There are specific difference somewhere, especially between P and D. But then right now, just know generally that the S energy is lower than the P energy, lower than the D energy, and lower than the F orbital. So in terms of energy, right? So, but if Aufbau is saying that if you are filling the electrons into this orbital, make sure you focus on the lower energy, fully fill them before you focus on the one with the higher energy. So you fill this one fully before you move to this guy. So you fill this one fully. When you are done, before you move to this guy, you make sure that this guy is fully ready before you move on to this guy. And this one is fully ready before you move on to this guy. That's what Aufbau is saying, right? So that's in terms of energy, right? That's what he is saying. So you have to know that if you are filling this, make sure you focus on the one with the lower energy before you focus on the next one. You focus on the next one, focus on the next one. If you have a p orbital, for example, that is having a degenerate orbital, right? This is px, py, and pz, right? These are degenerate orbitals. So we are going to focus on, it's not about fully filling it, but then make sure something is in the first one, second one, third one, like that, right? This is one orbital in general, but it just happened to be a degenerate orbital. So degenerate orbital almost have the same energy basically, but then we actually fill them from this one, this and this in that direction. Now let's look into the next principle. What does the next principle say? The next principle is Hund's rule of maximum multiplicity. Hund's rule of maximum, what is it saying? In filling of degenerate orbitals. So if you are talking about Hund's rule is going to focus on the degenerate orbitals. It means that the s orbital is not passed because s orbital is not a degenerate orbital, it's a non-degenerate orbital. So we are not going to focus on that. The focus will be on the degenerate orbitals, mean the p, the d, the f, right? They are the degenerate orbitals. And it's saying that if you are filling these degenerate orbitals, you have to singly fill them first with electrons of parallel spins before pairing them up with opposite spins. I'm going to use the p to illustrate what happened. This is a p orbital, right? And we say it takes a maximum of 6 electrons. So we are going to fill them with 6 electrons. So what Hund's rule is saying that if you are filling this degenerate orbital, right? So I have px, py, and pz. And I know that they have these sub-sections. So what I will do is I say they are singly filled first with electrons of parallel spins. Parallel spin means that my spin is going up, right? We've singly filled, this is how many sections? 1, 2, 3, right? So you singly filled first with electrons of parallel spins. So you go this one takes 1, you go to the next box of the same orbital, you fill it with the same electron, but the electron, you fill it with the electron, but that electrons will also be having the same spin or direction like the previous one. So this one also, you fill this one first, right? It's 1, 2, 3 before you come back and pair them up with the opposite spins. So then I'm going to fill them with the opposite spins now. Let me see what happened. Let me clean this and do it again. So I'm cleaning this. Let me use black this time, right? So if you are filling degenerate orbitals, what do? They say you have to singly fill first with electrons of parallel spins. This one should be parallel with this, should be parallel with this. You see all these are parallel, right? If you are having more sections, let's say the D or something, then we'll continue and continue. They should all be parallel first. When you get to the maximum and you know that in this orbital, you have reached the maximum, then you come back and now pair them up with the opposite spins. Opposite spins before you are done filling for this particular orbital. Hey, Mind you, p orbital doesn't have capsule. You see, just have 3, right? So this will happen. So if you just have p orbital quickly, you have 6 electrons. So you go parallel first, then you begin to pair up with the rest. Or I'm doing up first, so you guys think that it is always up. I can do this thing like this. I can do it like this, down, 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 but make sure that they are all parallel first. Parallel means they are following the same direction. Down, 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 or up, up, up. So depends on the one that you follow first. But then once you start with up, make sure you pair the rest up with the parallel spins before you go back and pair the other one. So if I'm going back, I will no more go down, I will go up with the parallel ones. And then my degenerate orbitals is pure. This applies to only degenerate orbitals. This applies to only degenerate orbitals. But if it is the s orbital, like you have the s orbital and you have 2 electrons, fill it and fill it. That's all. Just fill them first. Focus on filling this one first before you move to this one. And when you come here, this is where you play the game of distributing with parallel spin. You go back and fill the opposite spins. When you are done filling that p orbital, you move to the next orbital, which is d. You also do the same thing. D is also degenerate orbital. You have to fill it with parallel spins before you go back and pair up with the opposite spins, right? Yeah, that's how Hund's rule of maximum multiplicity is illustrated. And the last rule that we are going to have is the stability principle. And the stability principle is simple and saying that half of fully filled orbitals are stable. So if you have an orbital that is half filled or fully filled, that particular orbital is stable. Look at this. For the s orbital, right? This is an s orbital, right? It's half filled. Because s orbital is supposed to take 2 electrons in maximum, right? But it's having 1, so it's half filled. Or if it is fully filled, it's going to be what? It is fully filled. It's half filled or fully filled. When it's half filled or fully filled, that particular orbital is stable. That's stability. If you send this principle, this stability rule to the p orbital, so you go like this, right? This is a stable p orbital. It's a stable p orbital because p orbital is supposed to take a maximum of 6, right? But it is filled with what? 3. So 3 is half of it. So this particular orbital is half filled. But then, and so it is stable. But if you disturb the stability by introducing something more than half or less than half of it, then it's not going to be stable. This is not a stable orbital. Then you fill it, So if it is fully filled or half filled, then the particular orbital is stable. That's the stability principle. It applies for this degenerate, it applies to all the other degenerate orbitals as well. So these are the 3, or let me say 4 principles that govern this electronic configuration. Take time, go over this video, understand again, put your worries or concern in the comment section. Then we'll try to make it simpler for you if it's not simple in the subsequent sessions. Let's move on. We are getting closer to filling the electrons into the orbitals. I'm very happy that you are following and that you are gathering the concept alongside the journey. See you in the next session.